There are a number of details that go with Friedel-Craft's reactions that are worth discussing. One is their limitations, specifically that they don't work well on deactivated rings. Alkylation specifically has a couple of drawbacks, including the tendency to react several times and carbocation rearrangements. There's a way around both of these, which is to use something called acylation-reduction. We'll also want to look at some alternate reagents. There are a couple of different ways to do each of these reactions, both alkylation and acylation. And finally, we'll want to look at intramolecular reactions that occur in both of these types of reactions and can be relatively confusing. And thinking first about limitations, these reactions don't work well on what are referred to as deactivated rings. Deactivated rings are ones that contain a lot of electron withdrawing groups. So if we had a halogen and a nitro group, for example, it would be relatively difficult, if not impossible, to do an alkylation or an acylation on that ring. And this is not a terribly important one, we're just getting it out of the way first. It would only really come into play with synthesis, in that if we have a choice in the order of reactions that we want to do Friedel-Craft's chemistry before adding electron withdrawing groups, if possible. And we'll see examples of that in our synthesis section. The next drawback is that alkylation are prone to multiple alkylations. This is essentially a rate effect, and if we think about an alkylation, let's say, of benzene with ethyl bromide, and AlBr3. We usually use the chlorides for these, but we can use the bromide just as well. What would the predicted product of this reaction be? And we would normally predict, of course, that we're simply replacing a hydrogen with the alkyl group that's present, so everything in the reagent except the halogen. And we could take this one as an example. Whoops. So we have ethyl benzene. And when we think about the relative rates of reaction, this is actually going to be a faster reactant, or a reactant that reacts, let's say, reacts faster than benzene. That's because of all of the groups that we can add, the alkyl groups are the only groups that are activators. And there's a separate discussion on rates. If you've watched that or seen that already, then you'll understand what this means. If not, once you do, then that will help you make sense of this. But basically what it means is that the product of a reaction reacts faster or more quickly than the starting material, which means that once we've produced a significant amount of product, then that product actually starts reacting a second time. So let's say that we add another ethyl group on there, ortho to the first one. This reacts even faster, right? We have two activators, so that the reaction is even faster than before. So that means that once you have two groups on there, it's much easier to get a third. Once you have three groups on there, then of course it's just, we're inviting a fourth substitution reaction. So these reactions do have a potential drawback or limitation that they can overreact. It's sometimes hard to get them to stop at a single equivalent. And there are ways around this within doing an alkylation reaction, so we can still do these. We just want to be aware this is a potential limitation. Another important limitation to alkylation reactions is the potential for carbocation rearrangements. So let's say instead of making ethylbenzene, we wanted to make butylbenzene. What reagents do you think you would use to accomplish this transformation? A logical choice, of course, would be simply to use butyl chloride and AlCl3. Our rationale being that if we want this 4-carbon chain, the way to do it would be to take a 4-carbon chain, put a Cl on the end, and use aluminum trichloride as a catalyst. What we find out, however, is that rather than get the product that we want, we end up forming isobutyl chloride instead. And let's think about how that happens. Remember that our active electrophile in the alkylation reactions is our carbocation, and the carbocation that we would form from this particular species, and I'll put it in quotes because we may or may not even actually see it, that's a primary carbocation. So what we're more likely to see is one of two things happening. Either we form that carbocation simply because of the presence of the aluminum trichloride, and then it does a hydride shift, or while that carbocation forms, it rearranges. Either way, we're not likely to observe this primary carbocation that would lead to the product that we want, but instead we're likely to see that rearrange into a secondary carbocation. This particular rearrangement, again, is called a hydride shift because we're essentially moving a hydrogen with a pair of electrons, which we call a hydride. We could also have a methyl shift or an alkyl shift. And then this new carbocation acts like our electrophile. We're attaching that chain then by the positive carbon, which is not the end that we wanted, but rather one of the middle carbons. And so we get this compound, which we could call sec-butyl benzene, or better yet, 2-phenyl butane. Now, the way to avoid both of these limitations, potential multiple alkylations as well as the carbocation rearrangement, is to use a process called acylation-reduction. So what we'll actually do is to acylate our arene first and then reduce it to the alkyl arene that we want. Let's say, for example, that we're going to start with benzene, and that we want the butylbenzene we observed in the last example. The caveat, of course, is that if we try to alkylate, if we use 1-butyl chloride and AlCl3, for example, that we're likely to have a carbocation rearrangement and form an alternate product. And so what we do instead is we want a 4-carbon chain. We're going to add that chain, but as an acyl group. So we're going to make an carboxylic acid chloride instead of an alkyl chloride. So basically the same thing, but we just want to put a carbonyl on the same carbon as the chlorine. Those acyl carbocation intermediates are very stable, and so they tend not to rearrange. That means that we can get the chain on in the configuration that we want it in, with the attached by one end, and then all we need to do is to reduce it. We call it a reduction, of course, because we're replacing this oxygen with a pair of hydrogens, and reduction is the loss of oxygen and or gain of hydrogen. And there are actually two separate reactions that we can use to do this with, the Wolff-Kishner and the Clemenson. And it doesn't really matter which one we use when. One option is to use a zinc-mercury amalgam with hydrochloric acid, so we're either using a toxic heavy metal, mercury, or we can use a compound called hydrazine in KOH with a lot of heat. And so because we're cooking this really hot, you'll sometimes see a glycol solvent, like an ethylene glycol, for example, or a polyether. That's simply to attain the high temperatures necessary for the reaction. You don't need to put that necessarily, but since you may see it, we want to be aware of it. Now, we might think, oh, this is just a much better reaction than using a toxic heavy metal, mercury. And why wouldn't we do that? Well, hydrazine is also sometimes used as rocket fuel. And so if you can imagine then putting that on the stove and turning the burner on high and letting it cook for a couple hours, you can imagine the potential drawbacks to that reaction. That'd be one that you want to set up and then go to lunch for a while. What this allows us to do, though, is in 2 steps to accomplish the transformation from an arene to an alkyl chain that we might not otherwise be able to do using simple alkylation. Let's mention some alternate reagents, some other things that are sometimes used to make our reactions happen. And in thinking about these, it's important to remember that we're looking for alternate ways we could potentially generate our active electrophile. And one way, of course, to do that for alkylation, where our active electrophile is a carbocation, would be any other reaction that generates a carbocation. So we typically are going to see and if we, let's say we're making isopropyl chloride, we're adding an isopropyl group to the ring. We could also use an alkene with some acid to generate that carbocation. We could also imagine using an alcohol with an acid source. All of those would generate the same carbocation, which would then do our alkylation reactions. Now, typically for acylations, where we're using an acyl chloride, our active electrophile is the acyl cation. This acyl chloride, the most common alternative, and notice here we're simply adding a ketone group, so we've got our carbonyl and then a methyl. Common alternative to this reaction is to use what's called an anhydride functional group, where we have that same group that we want to add, but it is symmetrical in the sense that it has 2 of those carbon-containing groups on the flanking an oxygen rather than a chlorine. So the chlorine and that oxygen sort of play the same role, and if we wanted to think about a leaving group instead of the chloride as the leaving group, we'd actually have the oxygen in one whole side. Right? So if we did an acylation using acetic anhydride or this thing here, what we want to do is to take one side of our anhydride without the oxygen. That adds to the ring. And then we end up with the other side as a byproduct, specifically, typically, as the acid carboxylate or carboxylic acid. And that's important if those two happen to be tethered together. But if we see an anhydride, we want to do the same thing that we're doing with acylation of an acyl chloride. We just know that it's a little bit more complicated. And again, the chloride plays the role of our leaving group. We can think about this whole side also being a leaving group. The last complication in Friedel-Craft's chemistry comes from the fact that we sometimes will see intramolecular reactions, or reactions that happen within a molecule, a single molecule as opposed to between two separate molecules. So for example, let's imagine that we have benzene with this substituent attached. So we have a 4-carbon chain, actually 5-carbon chain with a methyl group and a chloride, or you could think about it as a 4-carbon chain with the final carbon having a 2 methyls and a Cl. And if we add AlCl3 to that, we can have a reaction that happens between the ring itself, which will act as a nucleophile, and the alkyl halide, which is going to serve as our electrophile. And remember, if we pull that chlorine off and make a carbocation, that's going to be our activated electrophile. And so it'll be this carbon that has the chlorine in it that's going to be attached to the ring. And that substitution is typically going to happen with a hydrogen that's ortho to this chain for 2 reasons. One is that that's the closest carbon in the ring, and this thing is having to twist around to bite itself in the tail. The other, of course, is that an alkyl group like that Ch2 is going to be an ortho-para director. And if that doesn't make sense yet, that's okay. There's a video on directing effects. But what we want to recognize is that we're going to substitute the carbon that has the leaving group adjacent to that chain, and we're going to bring along everything else. So we have the 2 methyls, and if we look at the rest of the chain here, we've got 1, 2, 3 carbons in addition to that red carbon, so we can simply add those dots and then play connect the dots, and we'll end up with this type of a ring. Let's look at another example. Let's say that we have this alkene, and we're adding sulfuric acid to it. Now this is a reaction that we could very easily confuse with sulfonation. So let's imagine that we're given the hint that we form a product with the formula C10H12. That means clearly we're not sulfonating because there's no sulfur oxygens present. So let's see what we can do. We'll shrink our first reaction, move it up out of the way. Thinking in terms of a nucleophile-electrophile combination, of course the arene itself with its pi system is going to be the nucleophile. And to make an electrophile, we want to consider that we have an additional pi bond far more reactive than the arene, and that we have an acid present. So our electrophile is going to be the protonated alkene. So if we think about this alkene picking up a hydrogen from the acid, that hydrogen would want to go to the end of the chain because that gives us a more highly substituted and therefore more stable carbocation. Now we've got the 2 carbons here from our alkene. Let's then keep careful count of our carbons. We have 2 more carbons than the ring. It's very easy to lose carbons or gain carbons in these reactions, so it's good for us to keep track of those. And now we can imagine that the ring reacts and picks up that carbocation carbon. Now if we want to, we can even draw that mechanism. We just need to use an alternate resonance form. We break this pi bond. Let's draw in the carbon atoms in the ring so we can keep careful track of what we have on each carbon. And that pi bond connects to the circled carbocation carbon. This carbon that I just put a square around is the only one that has a hydrogen attached. So that's where the substitution has to take place. And so if we redraw what we end up with next, we have the square carbon with its hydrogen. It's still connected to this other carbon from the ring. We have 1, 2 carbons with dots. Then we have the carbocation carbon, which we'll keep in the circle here, attached to our square carbon. Right, so we're forming this carbon-carbon connection. And that still has the Ch13 group, or the methyl group, that was at the end of that chain. So that gives us an intermediate. Of course, there's a carbocation present in the structure here because we have disrupted the pi system. And then we just need something acting like a base. Let's say the HSO4 minus that was produced when we protonated our alkene to come in to grab that hydrogen. We'll break the square carbon hydrogen bond, turn that into our alkene, or our 3rd pi bond in our arene. So we now have an aromatic system again. We have the 2 dot carbons. We have the circled carbon that was the secondary carbon of our alkene. And we have a methyl group. Now, of course, we still have this hydrogen that carried over from the very beginning. And so let's not forget that, so that when we go back and count hydrogens in our product to make sure we have the right formula, well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So that all checks out. And then if we count hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And so our formula works out, and we've managed to get the correct answer. Let's look at one more example, or 2 more examples. First, we'll take a carboxylic acid chloride that is attached to a benzene ring, and we will put a substituent, a methyl group here. We're going to react that with some AlCl3. Pause the video here if you want to and see if you can predict the product of this reaction. If we recognize our functional group here as a carboxylic acid chloride, that is going to be the source of our active electrophile. So that means that carbonyl carbon itself is going to be the electrophilic carbon. And if we remember, our ring is going to be nucleophilic. We're going to tend to substitute it in ortho position. And unless we have a really long chain, we're not going to be able to get a substitution further away from our original group than the ortho position. And let's make this a square. So we're going to connect the square carbon and the circle carbon. So our new bond is going to connect those two. And so we can draw our original ring. We want to include our square carbon. We have the carbon that has the chain on it, and then we add our circle carbon connected to our square carbon. We still have the carbonyl. Remember, the only thing we're losing is that chlorine. And then we have our 3-carbon chain from the position in the ring, ortho or adjacent to where our new substituent is added, and the carbonyl itself. And notice that there's one CH2 group attached to the carbonyl and one to the ring, and then in between there is a methyl group, and so our methyl ends up here. Now, from a standpoint of also thinking about alternate reagents, let's imagine a system where we start simply with a benzene ring and we're reacting an anhydride, but not just any ordinary anhydride, but a cyclic anhydride. So that we have, in this case, a 5-membered ring, and we use aluminum chloride. Take a few minutes here and see if you can predict the product. And what we'll want to remember here is that when we're using an anhydride as our source of our active electrophile, or our active electrophile, we're essentially making the oxygen in the middle and then one whole side act like our leaving group. And so that means that the carbonyl on the other side is going to be the point of attachment to our ring. So if we think first about just simply predicting the point of attachment and what that looks like, we're attaching the carbonyl. Just like acylation, we're bringing the carbonyl oxygen along, but then we're going to have 1, 2, 3 carbons in our chain, and then we'll have the rest of the anhydride. And we'll typically find that after our workup that's going to be protonated, but we wouldn't be wrong to think about that as a carboxylate, which, since there's technically not a proton source present in our reagents here, is simply what we would be ending up with. Now, from a synthetic standpoint, there's a reaction with SOCl2, which, if you remember from your organic 1, converts alcohols into alkyl halides. We'll later find out it also converts carboxylic acids into acid halides. So if we were to do that and then use aluminum trichloride, what would we get as a product here? Take a minute and see if you can figure it out. Noting, by the way, that this is a very tricky reaction and that you're really pushing the envelope here. So what we would again look at is the carbonyl from our acid chloride as our electrophilic center. The ring itself, again, is going to play the role of the nucleophile. And we have a question of regiochemistry here. We would normally think about this acyl group as being a meta-director, but there may or may not be sufficient room in the compound for it actually to reach around to the meta position. And so it would not be surprising to see this go to the ortho position, which is typical of these intramolecular reactions. So we'd have that carbonyl that's already attached to the ring. We have the circled carbonyl that was part of the acid chloride, And then we want to keep track of the fact that we have 3 carbons connecting those. And so our product here would actually be a 7-membered ring adjacent to our 6-membered ring. Now, it's not unreasonable to expect that that 7-membered chain could allow for meta substitution. And so we could certainly imagine that regiochemistry that we'd predict being followed with a 3-carbon system here. It would certainly be a strain system, but this would represent a reasonable answer as well. Now, the reality is that this chain here is going to be getting in the way of or bumping into this hydrogen, and would really actually need a longer ring, but that's not something that we necessarily know or understand at our level. So either of these answers would be acceptable. Each of these would be correct, but this would be what we'd more likely observe if we actually did the reaction.